3.7 Motion in a central field. Consider a single particle in a central potential. Its angular momentum is conserved. M vector equals r vector times p vector equals constant. Since constant m vector is perpendicular to r vector, the position is always in a plane perpendicular to m vector. Conservation of angular momentum has thereby reduced the problem from 3D to 2D. The appropriate form for the Lagrangian for motion in a plane with central potential is thus. See equation 3-24. Notice that there is no direct reference to the coordinate phi. In the Hamiltonian formalism, this means that. See the next equation. Thus, see equation 3-25.
Recall that the area of a radial sector radius r with angle of sweep phi is a equals 1 divided by 2 times r dot r phi, and the sectorial velocity is thus v subsectorial equals 1 divided by 2 times r squared phi equals m divided by 2. M is a constant, i.e. equal areas swept in equal times, aka Kepler's third law. As is typical in this type of analysis, integrals of the motion, e.g., conservation laws, are used as a first step to simplify analysis. Thus, for energy we have. See the equation shown, where the last term is the centrifugal energy. Rearranging. See the next equation. Integrating we get. See equation 3-26. Using d phi equals m over mr squared times dt.
See equation 3-27. Note, phi equals m means phi changes monotonically, so for a closed path that necessarily has a bounded minimum and maximum radius, we have for change in phase in going from the minimum radius to the maximum radius and then back. See the equation shown, where the limits of the motion are given by the energy having no kinetic part, where equation 3-28. The for there to result in a closed path must be exactly equal to or a multiple of must result in a multiple of, i.e. This only happens for all paths in the integral above when the potentials have the form or, and in those instances an extra integral of the motion occurs, known as the Runge-Lenz vector. Before moving on to the critical potential, however, let's consider the implications of non-zero angular momentum with a central potential. It is generally impossible to reach the center in such instances, even in attractive potentials. To reach the center when we are obviously considering a situation where we are not at the turning points of the motion, thus.
See the next equation. And regrouping and taking the limit as radius goes to 0, we find that the only potentials allowing this must satisfy. See the equation shown. This is only possible for minus potentials u of r equals minus alpha divided by r to the nth power with n is greater than 2 or with n equals 2 times n times alpha is greater than the fraction with numerator m squared and denominator 2m. In the preceding example we saw that the Kepler and Coulomb potentials, u of r equals minus alpha divided by r, were not in the group of potentials allowing motion through the center when angular momentum is non-zero. Let's now consider the attractive potential relevant for gravity, and for attraction between opposite charges, with u of r equals minus alpha divided by r in more detail. To start, the angle integral can be easily solved for this situation, where the effective potential is.
See equation 3-29.
Where the function minimum and significant energy domains are indicated in Figure 3.7. Figure 3.7. A sketch of the effective potential. U sub EF of Fmin equals minus m alpha squared over 2m squared. The motion is finite if E is less than 0, infinite if E is greater than or equal to 0. Integration then yields. See equation 3-30. Let's have phi equals 0 correspond to occurrence of nearest approach, perihelion, r sub min in what follows, in which case the constant is 0. Let's also relate to two forms of describing orbits: the set P, where 2P is known as the latus rectum, and E is the eccentricity, and the conic section parameters: the set AB, where 2A is the length of the major axis and 2B is the length of the minor axis.
See equation 3-31. To arrive at the orbit equation, see equation 3-32. From the orbit equation we can see that. See equation 3-33. Since 2A equals r sub min plus r sub max. See equation 3-34. We also see that the ratios B divided by R sub-min and R sub-max divided by B are risk-scale invariants and must be proportional to each other, where for E equals 0 this is shown to be equality, thus B equals the square root of R sub-min dot R sub-max, and we get C equation 3-35. Let's now consider the various cases in terms of the eccentricity parameter east equals the square root of 1 plus 2em squared over m alpha squared of the orbit.
For E equals 0 occurs when E equals minus m alpha squared over 2m squared. We have a circular orbit. R sub-min equals R sub-max equals P. For 0 is less than E is less than 1 occurs when E is less than 0. We have elliptical orbit. R sub-min is not equal to R sub-max. For ellipses and the circle we have bound orbits, which allows us to do the full sectorial integral of one such orbit, thereby getting simply the area of the ellipse or circle. Recall. See equation 3-36. Integrating over the time of one orbital period t. See equation 3-37. From this exact solution we can see that t squared proportional to the fraction with numerator 1 and denominator the absolute value of E cubed proportional to a cubed, which is Kepler's third law. For E equals 1 occurs when E equals 0. We have a parabolic orbit, unbounded, with R sub-min equals P over 2 times and times R sub-max equals infinity, which describes an infalling particle from rest at infinity. For E is greater than 1 occurs when E is greater than 0. We have a hyperbolic orbit, unbounded. The Laplace-Runge-Lenz vector. Consider an inverse square central force acting on a single particle that is described by the equation.
See equation 3-38, where
m is the mass of the point particle moving under the central force, p is its momentum vector, L equals R times p is its angular momentum vector, r is the position vector of the particle, figure 3.8, r is the corresponding unit vector, i.e., r equals r, and r is the magnitude of r, the distance of the mass from the center of force. The constant parameter k describes the strength of the central force. It is equal to gmm for gravitational and minus keqq for electrostatic forces. The force is attractive if k greater than 0 and repulsive if k less than 0. Figure 3.8. The LRL vector A at 4 points on the elliptical orbit under an inverse square central force. The center of attraction is shown as a small black circle from which the position vectors emanate. The angular momentum vector L is perpendicular to the orbit. The coplanar vectors p times L and mk/r are shown. The vector A is constant in direction and magnitude. The 7 scalar quantities E, A and L, being vectors, the latter two contribute 3 conserved quantities each, are related by 2 equations, a L equals 0 and A2 equals m2k2 plus 2 mel2, giving 5 independent constants of motion. This is consistent with the 6 initial conditions, the particle's initial position and velocity vectors, each with 3 components, that specify the orbit of the particle, since the initial time is not determined by a constant of motion. The resulting one-dimensional orbit in 6-dimensional phase space is thus completely specified.
Example 3.16. A test mass is released over the North Pole. A test mass is released at rest, 1 Earth diameter above the rotational North Pole. Ignore atmospheric friction. Use for acceleration of gravity near the Earth's surface 10m over sec squared, and for radius of the Earth R sub e equals 6,400 km. Find the velocity in meters/seconds of the mass when it hits the Earth. Find an expression for the length of time that it takes the mass to hit the Earth. Your expression should contain a dimensionless integral. Solution: a velocity at surface of Earth, the potential energy of the test mass, normal phi equals minus mg of m over r. Conservation of energy gives the kinetic energy to be the change in potential energy. See the next equation. B. Time until impact. Let's first get the relation for drop to radius r. See the equation shown.
Exercise 3.16. A test mass is released over the equator. Example 3.17. A planet of mass m. A planet of mass m orbits a sun mass m. We saw in the general properties of Keplerian systems that the planet moves in a plane containing the center of force A Introduce polar coordinates for the plane of motion and write the Lagrangian. B. Obtain the angular momentum and energy of the planetary system. And C. From the Keplerian analysis we know that the orbit is an ellipse, so relate the semi-major axis length a and eccentricity epsilon of that ellipse to the conserved energy and angular moment obtained in B, using the following parameterization of the orbit as an ellipse. See the next equation. Solution. A. We have from Newtonian gravitational force, and we shift to the center of mass frame. See the equation shown. For this we can write the potential energy as
U equals minus m sub t mu g over r. So, in polar coordinates the Lagrangian L equals t minus u. See the next equation. B. To get the energy, let's start with obtaining the equations of motion for the cyclic coordinates. Here the orbital angle to get other constants of the motion. Then use E equals t plus u. See the equation shown. C. Relation to parameterization of an ellipse. At our sub-min and our sub-max we have r equals 0, so get. See the next equation. From the ellipse parameterization we have for our sub-min and our sub-max. See the equation shown. Using with the two equations for energy at the max and min our positions we get. See the next equation.
Substituting the relation for L squared into the two energy equations, as well as our sub-min equals a times 1 minus epsilon, and our sub-max equals a times 1 plus epsilon, we get. See the equation shown. Thus, see the next equation. And substituting into the L squared relation we regroup to the get expression for eccentricity. Epsilon equals the square root of 1 plus 2 EL squared over mu alpha squared. Exercise 3.17. What is the eccentricity of the Earth-Moon system? Of the Earth-Sun system? Example 3.18. A particle of mass m. A particle of mass m moves in a potential U equals alpha over r minus the fraction with numerator beta and denominator r cubed. Alpha beta is greater than 0. A. For what range of radii are circular orbits stable? Express the condition on r in terms of alpha and beta. B. Find in terms of r, alpha, beta, and m the frequency omega of a circular orbit and the frequency w of small oscillations about a circular orbit.
Solution. A. U equals alpha over r minus the fraction with numerator beta and denominator r cubed. Alpha beta is greater than 0, and for orbits, L equals 1/2 m times r bar squared plus r squared theta squared, minus U and E equals 1/2 m r squared plus the fraction with numerator m sub theta squared and denominator 2m r squared plus U. Thus, see the equation shown. Circular orbits for. See the next equation. Stable orbits for. See the equation shown. B. Recall the area swept. A. Relation. M sub theta equals m r squared theta equals 2m dA over dt. Then can write. See the next equation. The frequency of the circular orbit, normal omega, is.
See the equation shown. And the frequency of small oscillations about that circular orbit. See the next equation. Exercise 3.18. What happens when alpha and beta dot are selected such that normal omega equals omega? Example 3.19. Particle in a central force field. A particle moves in a central force field given by the potential U equals minus k, the fraction with numerator e raised to the minus r over a power and denominator r, where k and r are positive constants. A. Find the relation between r, L, and E for circular orbits. B. Find the period of small oscillations, in the r theta plane, about a circular orbit. Solution. A. So, have U equals minus k, the fraction with numerator e raised to the minus r over a power and denominator r, and L equals 1/2 m times r squared plus r squared theta squared minus U. For the centrifugal barrier we have.
See the equation shown. So, see the next equation. And the equations of motion are. See the equation shown. Have circular orbits r equals const4. See the next equation. B. We have omega equals the square root of 1 over 2m times the fraction with numerator partial differential squared U sub EF of f and denominator partial differential r squared, and U sub EF of f equals the fraction with numerator positive L squared and denominator 2m r squared minus ke raised to the minus r over a power over r, and at oscillation equilibrium. see the equation shown. Thus, see the next equation. From see the equation shown, we can then regroup to get see the next equation.
Exercise 3.19. Suppose the fraction with numerator partial differential squared u sub ef of f and denominator partial differential r squared vertical bar sub r sub c for some choice of k and a. Derive frequency formula to third order derivative and potential. What is the new oscillatory frequency? Example 3.20. Kepler's third law from Newton's laws. A. Show directly from Newton's laws that, for two stars of mass m1 and m2 in circular orbits about their center of mass, Kepler's third law has the form t squared equals the fraction with numerator 4 pi squared and denominator g of m sub 1 plus m sub 2, r cubed, with t the period and r the distance between the stars. B. Show that the formula can be rewritten in the form t squared equals m sub 1 plus m sub 2 to the minus 1 power times r cubed, with t in years, r in astronomical units, and m in solar masses. If r is the semi-major axis, this holds for elliptical orbits as well. C. Show that for a small object in circular orbit at the surface of a large object, t equals k rho raised to the minus 1 over 2 power, and find the constant k. What is the period of a pebble in orbit at the surface of a spherical rock? Rho equals 3g of /cm cubed. Solution. A. Recall, L equals R times mu V equals CO and ST and dA equals 1/2 R dot R d theta. So,
see the equation shown. 2 mu dA equals L dt 2 mu of pi AB equals LT. Recall the relation of masses to the major and minor axes. See the next equation. Thus, see the equation shown. Thus, substituting for A equals R evaluation on semi-major axis. See the next equation. B. Unit change goes as follows. See the equation shown. So, t squared equals m sub 1 plus m sub 2 to the minus 1 power times r cubed k, and k equals the fraction with numerator 1.5 times 10 to the 8th power km cubed times 4 pi squared and denominator 6.67 times 10 to the minus 11 power, and the fraction with numerator m squared and denominator kg squared times 3.15 times 10 to the 7th power secant squared times 2 times 10 to the 30th power kg times open bracket the fraction with numerator m sub normal theta dot y r squared and denominator au cubed close bracket equals 1.0 times open bracket the fraction with numerator m sub normal theta dot y r squared and denominator au cubed close bracket.
Thus, see the next equation. C. T squared equals m sub 1 plus m sub 2 to the minus 1 power times r cubed asymptotically equals m sub larg of e to the minus 1 power r cubed asymptotically equals the fraction with numerator 4/3 pi r cubed and denominator m sub larg of e times 1 over 4/3 pi equals rho over 4/3 pi. Thus t equals k rho raised to the minus 1 over 2 power, where k equals 1 over 2 the square root of pi over 3, where t is in units of years, r equals au right single quotation mark s. M equals m sub normal theta prime s, and m sub 1 is much greater than m sub 2. For rho equals 3g of /cm cubed equals 3 times 10 cubed kg of /m cubed. Thus, see the equation shown.
Exercise 3.20. What is the period of a pebble in orbit at the surface of Earth? Rho equals 1g of /cm cubed, and at the surface of a neutron star, rho equals 10 to the 16th power g of /cm cubed. Example 3.21. Binary systems. Stellar masses are found by observing binary systems. Typically one cannot resolve the stars, but the spectrum shows two periodically changing Doppler shifts, giving the line-of-sight velocity of each star. Call the velocities v sub 1 and v sub 2. Show that if the orbit is inclined by an angle theta to the line of sight, r equals v sub 1 plus v sub 2, divided by normal omega sine theta, and m sub 2 divided by m sub 1 equals v sub 1 divided by v sub 2, and the fraction with numerator m sub 2 cubed and denominator m sub 1 plus m sub 2, squared sine cubed theta equals a sub 1 sine theta, cubed divided by t squared. Start with v sub 1 equals inverted ohm sub 1 the sine of theta times v sub 2 equals inverted ohm sub 2 sine theta, where inverted ohm sub 1 equals r sub 1 normal omega times inverted ohm sub 2 equals r sub 2 normal omega let r equals r sub 1 plus r sub 2. Then, v sub 1 plus v sub 2 equals inverted ohm sub 1 plus inverted ohm sub 2 times sine theta equals r normal omega sine theta r equals v sub 1 plus v sub 2 divided by normal omega sine theta.
With the origin at Cm, m sub 1 r sub 1 plus m sub 2 r sub 2 equals 0 and m sub 1 inverted ohm sub 1 plus m sub 2 inverted ohm sub 2 equals 0, thus, the absolute value of m sub 1 v sub 1 divided by sine theta equals the absolute value of m sub 2 v sub 2 divided by sine theta. And the fraction with numerator m sub 2 and denominator m sub 1 equals the fraction with numerator v sub 1 and denominator v sub 2 to get the last relation. Recall that on the semi-major axis, for r. See the next equation. Thus, see the equation shown. From which we get. See the next equation.
Exercise 3.21. Binary with neutron star. Consider a binary with one neutron star. The observed Doppler shift of the neutron star has magnitude normal triangle lambda over lambda equals 2 times 10 to the minus 6 power and a period of 4 days. If the mass of the neutron star is less than 3m sub normal theta, what is the maximum mass of its companion? Example 3.22. Motion inside a paraboloid of revolution. A particle of mass m is constrained to move under gravity without friction on the inside of a paraboloid of revolution whose axis is vertical. Find the one-dimensional problem equivalent to its motion. What is the condition on the particle's initial velocity to produce circular motion? Find the period of small oscillations about this circular motion. Let's adopt cylindrical coordinates x equals rho sine theta y equals rho cosine theta, in which case we have coordinates z equals a over 2 rho squared equals x squared plus y equals x squared and potential u equals mg of z. Thus, the Lagrangian is, see the equation shown, where, see the next equation, thus,
see the equation shown. Using the Euler-Lagrange equation for theta. See the next equation. Thus, see the equation shown. Using the Euler-Lagrange equation for rho we get. See the next equation. Circular motion rho equals 0. See the equation shown. Thus, see the next equation. Let's now consider small oscillations for. See the equation shown. Let rho equals rho naught plus eta, then retaining terms to first order in eta. See the next equation. Thus, see the equation shown. Exercise 3.22. In fall time. Two particles move about each other in circular orbits under the influence of gravitational forces, with a period t. Their motion is suddenly stopped, and they are released and allowed to fall into each other. Show they collide in time t divided by 4 the square root of 2.
Example 3.23. Attractive central force. As show that if a particle describes a circular orbit under the influence of an attractive central force directed to a point on the circle, then the force varies as the inverse fifth power of the distance. B. Show that for the orbit described the total energy of the particle is 0. C. Find the period of the motion. D. Find x, y, and v as a function of angle around the circle and show that all three quantities are infinite as the particle goes through the center of force. Solution. A. Start with position given by r minus 2 a sine theta f of o r times 0 is less than or equal to theta is less than or equal to 180 degrees. And have Lagrangian. See the next equation. Then, see the equation shown. Use r squared plus r squared theta squared equals 4 sub a squared the cosine squared of theta squared plus 4 sub a squared the sine squared of theta squared equals 4 sub a squared theta squared for the constraint on r to identify the respective force. Similarly, we get E equals 2ma squared theta squared plus u of r equals integral of motion so constant.
See the next equation. Thus, see the equation shown. Indicates that the attractive force is. See the next equation. B equals 2 a squared m sub theta squared over mr to the fourth power minus the integral from infinity to r of minus 8 a squared m sub theta squared over mr to the fifth power equals 0. C T equals question mark m sub theta equals m of r squared theta equals m of, for a squared, the sine squared of theta d theta over dt. Dt equals m of, for a squared, the fraction with numerator sine squared theta and denominator m sub theta d theta.
T equals the fraction with numerator 1 and denominator m sub theta, the integral from 0 to pi of, for a squared, times m the sine squared of theta d theta equals the fraction with numerator 2 pi ma squared and denominator m sub theta. Alternatively, m sub theta equals m r squared theta equals m r d theta over dt equals m2 dA over dt vector dt equals the fraction with numerator 2m dA and denominator m sub theta vector t equals the fraction with numerator 2 pi ma squared and denominator m sub theta. Dx equals or cosine theta equals 2 a sine theta cosine theta equals of the sine of 2 theta times x equals 2 a times cosine squared theta minus sine squared theta times theta. Y equals or sine theta equals 2 of the sine squared of theta times y equals for a sine theta the cosine of theta theta. So, see the equation shown, and see the next equation.
Exercise 3.23. Particle in central harmonic potential. A particle of mass m moves in central harmonic potential v of r equals 1 divided by 2 times kr squared with a positive spring constant k. A. Use the effective potential to show that all orbits are bound and that E sub min must exceed the square root of kl squared divided by m. B. Verify that the orbit is a closed ellipse with the origin at the center. If the relation E divided by E sub min equals hyperbolic cosine of 11 defines the quantity 11, show that the orbital parameters for A, B, and eccentricity. Discuss the limiting case E vector E sub min and E is much greater than E sub min. C. Show that the period is independent of E and L.